Okay, so for the next unit, we're going to talk about this idea of relative motion. Okay, this is in chapter 4. It's not the end of chapter 4, but we're going to save the rest of that chapter for another unit. So this will conclude chapter 4 for our purposes. Okay, and so the idea of relative motion is simple. It's essentially looking at the motion of an object relative to another object. So to get a better idea of that, let's imagine a bus. Okay, so we have a bus that's moving along the road, and we'll put a couple people on the bus. We'll say there's one person standing at the back of the bus, and there's a person sitting in the front of the bus. Okay, we'll call this person standing person A. The bus itself is person B. And so the person sitting on the bus also represents the reference point B, because that person is stationary and fixed to the bus. And then we'll put one more person standing on the side of the road, and we'll call this person G, because that person just represents the ground. They are fixed relative to the ground. Now, if we have the bus, and let's say that the bus is moving with a velocity of, we'll say 10 meters per second, and then we'll say the person on the bus is walking forward at 2 meters per second. Okay, then if you're the person on the ground, what do you see as the velocity of person A? Okay, because if the bus is moving forward, the bus is moving at 10 meters per second, and then we see person A moving at an additional 2 meters per second on the bus. So that means that the person on the ground would see person A moving at 10 meters per second, the speed of the bus, plus the additional 2 meters per second. So on the ground, or relative to the ground is what we would say, we would think the person's moving at 12 meters per second. Okay, it's like the bus itself gives the person an added 10 meters per second. The person didn't have to do anything to get that extra 10. They just had to be on the bus. Okay, and the same thing works the other way. But this time, person A is starting at the front of the bus. Okay, and so we have all the same reference points. Okay, and we'll give it all the same numbers. B is moving forward at 10 meters per second, but now person A is moving to the left at 2 meters per second. So how fast would a person on the ground think person A is moving? Rather, how fast is person A moving relative to the ground? Well, in this case, person A, being on the bus, is moving at 10 meters per second to the right, but then they're also walking 2 meters per second to the left. So on the ground, we would think they were moving 8 meters per second towards the right. They're still moving forward through space because they're not moving faster than the bus containing them. Okay, and this is the idea of relative motion. So in one dimensions, it's kind of a fun little game to play, but it's more applicable when you're doing 2 dimensions. Okay, so we need to set up some kind of formula for this. So it looks something like this. If we have 3 numbers, okay, let's say you have a bird, so I'm just going to draw a dot, and let's say that this dot represents a bird. Okay, the bird can fly through the wind, so we would say this is the velocity of the bird relative to the wind. Okay, so, and I'll do these in colors so we can see this. This would be the velocity of the bird relative to the wind, or a better way to say that would just be the air. Okay, so now let's take away the B and W here and put it in the colors. So the bird was in red and the air was in green. I said W. You can keep a W if you'd like, but I'll just say A for the air. So that's what this notation means. It's the velocity of the bird relative to the air. Now the air might be moving in some way. Maybe it's moving like this. Okay, and so it has a velocity. So this would be the velocity of the air relative to the ground. There we go. Because we would measure the wind speed as if we were standing on the ground with something to measure the wind, and this is how fast it moves relative to the ground. So then the question would be, if I'm an observer on the ground, I want to know how fast, so what is the velocity of the bird relative to the ground? Because from the ground, what would you see the bird do? If the bird was flying to the right and there's a wind pushing it up, we would see, so let me draw it down here so I've got some room. So we know the bird is moving to the right. We know the wind is pushing up on the bird. So the path we would see the bird take would be at a diagonal, because the bird has a horizontal velocity and the wind provides this vertical velocity that pushes him off at some angle. So from the ground, we would think the bird's flying intentionally at this angle, when really it's the result of these added velocity vectors. So the general formula we would write for this, and there's kind of a trick. You'll notice that we have velocity of bird to ground, we have velocity of the air to the ground, and of the bird relative to the air. So notice the two letters that we are looking for. Velocity of bird to ground. Okay, also notice the B is on the left, the G is on the right. Okay, so if you look at our labels, okay, it's suffice to say that if we're trying to get V with B to G, so from left to right, the B should be on the left side. So in other words, I can write this as VB to the air. Okay, and then I'm going to say plus velocity of air to ground. Okay, now I know that's a little confusing, but the idea is, what is the letter that's missing from my final answer? I'm looking for bird to ground, but notice there's no A label in that. And so one of the ways to kind of think about it is, when you write out your formula, you want to do it in such a way that if I take the B and the A and the G, and I merge these together, okay, I sandwich out the A. And so as a result, what do you get? I mean, if I write them all together, it's B, A, G, but those A's get sandwiched out, and so then I get my BG. Okay, that's what we're trying to do. So that's kind of the way to think about, how do I set up the formula? Okay, and once you've got the formula set up and you're using vectors, if you use the I hat, J hat notation to denote your vectors, these problems are actually very, very simple. Okay, let's do a quick example of that. So we'll stick with what we were talking about with the bird. Okay, we'll say the bird can fly through the air at, make up some numbers, say 3 meters per second. We'll say that there is a light breeze going to the north at 2 meters per second. And so we want to know, what is the velocity of the bird? One sec. There we go. The velocity of the bird relative to the ground. Okay, so if we're going to write out a formula for that, we would have the velocity of the bird relative to the air plus the velocity of the air relative to the ground. Okay, and again, each of these is a vector. Okay, so let's write these out as vectors. What is the velocity of the bird relative to the air as a vector? Well, the bird's velocity was 3 meters per second, in the positive x direction. So this would be 3 meters per second I hat and nothing in the j hat. Now I wouldn't have to write 0 here, but I'm going to write it now just so we can kind of see how these combine. The velocity of the air to the ground would be nothing in the I hat and a positive 2 meters per second in the j hat. So that means the velocity of the bird to the ground, okay, would be the sum of these two vectors. So the bird relative to the air plus the air to the ground. Now again, if we add vectors, we can only add like terms. Okay, so 3 plus 0 would just mean 3 meters per second in the x direction, and 0 plus 2 would mean 2 meters per second in the j direction. And so this is our answer. The velocity of the bird relative to the ground will be 3 meters per second in the x direction and then 2 meters per second in the y direction. So typically, though, the problems are not going to just ask for that. They're going to want to know what is the speed of the bird to the ground, or rather the magnitude. So remember, the magnitude of these vectors would be using Pythagorean theorem. So that'd be the square root of 9 and 14, or excuse me, 9 and 4, which would be 13, square root of which is 3.6 meters per second. Okay, and if we want to know the angle, the direction, we would do the inverse tangent of opposite over adjacent. So that's 2 divided by 3. And then we want to do inverse tangent. And that would give us an angle of right around 34 degrees above the positive x. So if we were on the ground looking up at the bird, then we would think the bird is actually flying at an angle of 34 degrees at a speed of 3.6 meters per second. Okay, so that's the idea of relative velocities. Okay, and you're going to get a lot of examples that deal with different forms of this. So we'll do one more. So in this example, imagine we have banks of a river. So we've got water flowing in the river, and we'll say that the water has a current that gives it a speed of 2 meters per second. Okay. Now, someone on the side of the river notices a log in the water and notices that the log moves at an angle towards the bank. And they measure the speed to be, we'll say, 6 meters per second. Okay, at an angle of, we'll say, 20 degrees. All right. So this person then questions, how fast is the log moving in the water? Okay, so if we label all of these velocities, all right, we'll start with the water. This 2 meters per second represents the velocity of the water relative to the ground, because we're standing on the bank and we notice the water's moving at 2 meters per second. Okay, the 6 meters per second in the water, this is what the person observed the boat doing in the water. So notice we have these 3 different velocities here. Oops, I didn't mean to write boat. Hang on a minute. Not boat. The 6 meters per second is the velocity of the log to the ground. And the velocity of the log to the water is what we're looking for. So we've got 3 different velocities here. So now we have to think, how do we arrange them so that we see the variable that gets sandwiched out? Well, if you notice, let's start with the log variable. So if I look at the L's, I see an L on the left and an L on the left, and that's it. So that would mean that the L has to be on the left side no matter what. I then see a G on the right and a G on the right, so the G must be on the right no matter what. But then notice the variable we use for the water, let's do a different color. The variable we use for the water, for here it's on the left, but here it's on the right. So because they're on different locations, one's on the left, one's on the right, that must be the variable that gets sandwiched out. Okay, so think about a sandwich. The W represents the meat, and the L and G's are the breads. So if we write out our formula now, I see velocity of LW, log to the water. I then see velocity of water to ground. And if I sandwich out the W's, I get the velocity of log to ground. So there is my relative motion equation. Okay, now if we were to write this out in IJ notation, we don't know what the velocity is of the log to the water. That's what we're looking for. But the velocity of the water to the ground, well, 0 in the x direction and a positive 2 in the y direction. And the velocity of the log to the ground, well, that's going to force us to do some trig. The x component is the horizontal component of this triangle. The y component is the vertical piece. So we take out a calculator and we look at what 6 cosine of 20 is, and we get 5.6 meters per second in the x direction. And then if we do 6 times the sine of 20, we get right around 2.1 meters per second. Okay? So, if we're going to solve this for the log in the water, it shouldn't take much to see that we're just going to subtract this whole vector over to the other side. Okay? And so when we do that, we see that the velocity of the log in the water, if I subtract down the x's, 5.6 minus 0 is 5.6 meters per second in the x direction, and in the y direction it's about 0.1 meters per second. And so there is the velocity of the log in the water. And we could go the next step with what is the speed and direction, but that's repeating a step. You know how to do that.